So my name is Daniel Söderberg. I'm the director of Treesearch, but primarily I'm the researcher within Wallenberg Wood Science Center. And one of the things we have been doing for a long time is working with nanocellulose and try to do spinning of nanocellulose fibers. So the presentation will deal with this, and the starting point is very similar to my background. The question is, what can you make if you really are looking at the potential of the biomass we have in the Swedish and forests globally? And of course, the reason is this is one more picture of trees, because there's a lot of trees in the world. We are having an increased amount of trees in Sweden, and we are finding new ways of making use of this material. And the starting point for this idea was also the starting point of the Wallenberg Wood Science Center, which was then started in 2007. And it's multidisciplinary. I'm working with fluid physics from mechanical engineering, but there is a lot of chemists and it's biotechnology. So it's a very wide research base. We want to have an international position in wood science, and it's a fantastic opportunity provided by the Knut and Alice Wallenberg Foundation for 10 years, and that has been extended for 10 more years, almost twice the turnover. And it's this time not only Knut and Alice Wallenberg Foundation, but also funding from industry and through the universities. Starting with that, what we're trying to do is to make use of the components of wood. And I guess most of you have seen this type of illustration before. But what we're interested in is the smallest scales of components. So we're not interested in the trees, we're not interested in the logs, we're not interested in the cellulose fiber, but we are interested in the cellulose nanofiber, which is typically 5 to 10 nanometers diameter and roughly 1 micrometer in length. And this is an interesting component that we want to start with. And you can take it out of the tree, and that is something that has been developed during the last 2 decades. More efficient processes of extracting nanocellulose, and it's just interesting to look at it from the left image. You can actually see nanocellulose as a very low concentration suspension or dispersion, and it behaves like a gel. And this is actually the starting point we have, because what you can do, and this is not my area of expertise, I'm working closely with Professor Lars Wågberg at Royal Institute of Technology. One possibility that you really can utilize is the possibility to control surface charge and electrostatic screening. So you can control the rheology of nanocellulose, not only by concentration, but also controlling the electrostatic environment and the charges. And this is just trying to illustrate this possibility. To the left, we have a TEM image of cellulose nanofibers. They are very small. It's hard to make them behave as you want to. But one thing you can do, and that is shown to the right. The rightmost shows a concentration of 3 grams per liter. That's 0.3% nanocellulose dispersions at pH 7. And by inducing gelling through lowering pH, you can actually freeze this into something that has a gel-like structure. So this was the starting point, for example, for Andreas Walter, that started to work with wet spinning of cellulose nanofibrils. And the idea is that you have your liquid nanocellulose dispersion and you eject it into a bath. And the bath can be ethanol, dioxane, isopropanol, or salts or acids. And what it does is induces this gelling from a liquid state to a solid state, and then you get a filament. And what they showed was the possibility of making advanced functions. You can take nanocellulose, 100% nanocellulose, you can make filaments, and you can start to add functionality. And this was something that we looked thoroughly on, and of course, being from the fluid mechanics side, we had an idea on how to do this as a continuous process, not using a syringe. And what we used was something called flow focusing, which is very popular in microfluidics. The idea is that you have a channel, and the channel actually is a cross. In one of them, you enter your nanocellulose dispersion. It's the Q1 in this image to the left. And you inject that together with liquid streams coming perpendicular, and what this does, it forms a nanocellulose gel thread. It's about a system that is easily to design. The choice of 1 millimeter was purely accidental, and the only thing that our workshop could do at the time. So this was something that we put together, it's 8 years ago. And by doing this properly, you can actually manufacture filaments. So what we see here is SEM images from today, Dr. Carl Håkansson's thesis, when he showed that you can make excellent filaments, and you can see that you can even make knots. These are 100% cellulosic, and they are based on this microfluidic design. What we came out was a very strong focus on mechanical properties, and this image is taken from the Nature Materials review, and it shows specific stiffness and specific strength. And this is an Ashby plot, which everyone working with materials should be aware of how it works. What it shows is how a material behaves in proportion to its weight. So this is the system you should look at, or this graph is the one that tells you if you're going to do anything good with lightweight construction. And here we have tried to depict the behavior of the filaments that Carl spun using this red circle with a picture of the filament end in the center. And then we're comparing to other natural materials. And we are fairly good. We are on the level of, from strength, which is the vertical, we are on the level of silk, and stiffness-wise, we're not on the level of Kevlar or carbon fibers, but we are fairly good when it comes to mechanical performance. And then the question, of course, arises, if we want to do this, what should we do? Which type of product or material should we make? And we're starting with the tree, which is a very high value. The Christmas tree is at least kind of high value trees. And then we want to make high value products. And of course, you could do a lot of textiles, but the process we had was very slow. So we're primarily been looking then at high performance materials like glass fibers, which are used in windmills. If you want to make a wind power field, you can actually use glass fibers today, but you would like to have something that is biodegradable eventually, because glass fibers cannot be recycled properly. And of course, you have this high performance bulletproof vest to the right. So the question was where to go. And it turns out to be a question of processes. And this is a very simple illustration of the main challenge we had of trying to make strong filaments. And I call them filaments. They are continuously spun threads of nanofibers. And the flow focusing device, what it manages to do is through the acceleration that we have in the center, you align these nanofibers and you cause the gelling. And what you're always battling is Mr. Brown, which is the red figure to the bottom right. The Brownian motion does everything it can to take away alignment. Because nanofibers are nanoscale, Brownian motion will be very important. This is a very big difference from example, if you compare to paper making, where the fibers are so big, so Brownian motion is something you don't have to care about. For this case, with nanoscale fibers, Brownian motion is important. As a matter of fact, if you look at a cellulose nanofiber in liquid, in a system where it doesn't interact with other nanofibers, it will rotate around on the scale of milliseconds. So this is our main, or the key part that we need to battle to get good alignment and good properties. So this is a process development step that we took that was necessary. And this is trying to just depict the behavior with this Brownian motion, and which this is the first challenge. So this is simulations of nanofiber behavior, and the first one we have is, and I hope that this plays out decently, is a single nanofiber. And as quickly as you have a lot of them, they are starting to interact. So what we have is a system of nanofibers where we are doing everything we can to get them all aligned in one single direction. So this is the challenge we had that we met with Carl. We could do it for short fibers, but we started to realize that if you want to do this bulletproof vest, and if you want to do these windmills, we need to produce filaments continuously. We also realized that one of the keys is, of course, efficiency. And energy demand for drying filaments turned out to be a big part of it. Can we produce larger volumes because no one is interested in 1 centimeter of a filament? And the last part, which I will start with, can we functionalize? Can we add other components or behaviors, or can we make devices with these? And this is following up what was shown by Andreas Walter. One of the first things that were made was functionalization for conductive fibers. So this was done by Max Hamedi and co-workers. And what was done was adding carbon nanotubes to the cellulose nanofibers. And by doing this, you could make conducting filaments. So what we have is the filaments to the left with the SEM images, and to the right, you can see how they are powering a blue LED light. So this is one functionality that is possible. You can actually intermingle a component that is about the same size as the cellulose nanofiber to make a hybrid material. Something else that was tried or pursued was adding smaller components, and this is the case with silk. And this is spider silk, recombinant spider silk, that was done together with Professor My Hedhammar at KTH. And what we did was add a small amount of spider silk to our filaments. And spider silk, these proteins are much smaller than the fibril or nanofiber, which is different from the case with the carbon nanotubes. So when we have the smaller components, they adhere to the surface of the nanofiber. And by doing this properly, you can actually achieve two things. Bioactivity. The silk gives you a possibility to support cell growth. And this is what is shown in these two images. To the left is a pure CNF fiber. To the right is a CNF together with recombinant spider silk. And the green fluorescence means that you are supporting cell growth, which is then a possibility to use as a biotechnical device, or for use, for example, to make ligaments or tendons. It also, one possibility that we pursued is just continuing to improve mechanical properties. And this is, of course, a set of stress strain curves, which is showing behavior. What is interesting here is by varying the properties of cellulose nanofibers and actually the values behind CNF 550, 820, and 1360 is the surface charge. And by controlling the surface charge, we are controlling the mobility and length of the nanofiber, which actually influences the stress strength behavior quite significantly. We can also see that the fibers at different relative humidities behave differently. That is the center graph. And it shows that at 50% relative humidity, we have one behavior, and it's very dry, the fiber becomes the filament becomes very, very brittle. And to the rightmost one, we are functionalizing by BTCA, which is just giving us cross-linking between the nanofibers, and that gives us even better mechanical performance. This was, of course, an interesting step that was taken. It was done and had a quite good impact, I have to say, and we are very proud of being part of this. But the challenge is still there. So far, we have made filaments, and we have solely focused on potential. So the next challenge we have is, of course, how do you do this continuously? And can we produce larger volumes? And what we want then is a continuous processing for making strong filaments. Something that we have spent a lot of time in doing is trying to understand the process by doing a lot of significant work using synchrotron radiation sources. And the reason is, if you're using these type of sources, you can actually understand what happens in your processes. This is not possible with microscopes, and it's not possible with a lot of the lab scale equipment. So this time resolution that we can get from synchrotron sources is something that we have used extensively, and that has helped us to take us a couple of steps. This is one step. So if you remember the first sort of image of this microfluidic channel, it had 2 flows from the sides, and this one has 3 flows from the side. And as it turns out, this actually, it came from an idea of functionalization. If you look at this image, you can imagine that you have your cellulose nanofibers in the center, and then you have different flows coming in that is accelerating and aligning your nanofibers. And then you can start to add different components in these flows, so you can functionalize. However, this setup turned out to be a fantastic process improvement. Because if you do it with a gelling system, you don't want to cause blobs or gel blobs building up in the system. And in the setup you can see in this image, the first flow coming into the nanofibers is just pure water. And the pure water makes it impossible for the second flow, which is the gelling agent, which could be acid or salt, to come in direct contact with the nanofibers and at the same time any solid surfaces. So this setup that was made for something totally different became the perfect process development. Using this, you can run the flow focusing device for hours without a problem. And what we did then was develop the potential using this. We can move even higher. We can start to battle with, maybe not really, but we're on the level of Kevlar for stiffness. We are coming closer to Kevlar and carbon fiber for strength. We are better than dragline silk, but we still are battling with the idea of continuous processes. And to do a process, you need to, we can do as we did with this 2-flow system that I showed just a moment ago. You can either know what you're doing or you can just get lucky. And we were lucky, but we are gradually developing our knowledge. So we today understand the rheology. We think that we understand the internal structure, and we understand this interaction between the fibrils or the nanofibers. So we are taking these all steps and we're starting gradually to know the system. We have realized that when you do this type of potential of strength that we have looked at, we have realized a couple of things that are weaknesses. We have seen strong effects of variations of the CNF. And that is actually quite poorly understood generally. The material is primarily defined. I mean, what we do is we take a CNF, we make a batch of cellulose nanofibers, we spin filaments, and it turns out to be very dependent on the batches of the CNF. So we're battling with getting proper constant behavior or properties of the nanofibers. And there's a lot of reasons behind these variations. We have annual variations of the wood natural material, which is also a geographic variation. And the pulping process is naturally sort of inducing variations, since everyone working with pulps know that they are not exactly the same from day to day. And then we have an effect of pickup and drying. And I want to make a sort of excursion on the challenge that we're seeing. So looking back to the digital revolution, you can start to think about how did it come about? And this is a little bit of a boring slide with a lot of text, but to the right, we have the contact point transistor developed by Bell Labs. And this is based on a sort of the semiconductor effect. And that is something that was known from the early 19th century. 1947, the device to the right was developed. That's the point contact transistor that also gave a Nobel Prize. It was developed at Bell Labs. One of the problems they have was actually the possibility to make constantly the same behavior. You had to do a lot of devices to get proper behavior. Everyone didn't work. That was developed further 54 with the silicon junction transistor, still bulky and difficult to manufacture on a large scale. But then came the interesting part, which we're sort of looking into from the manufacturing of the perspective of processes for making filaments using microfluidics. When it comes to the transistor, the surface passivation process that was developed by Attala in 1958, so that's 11 years after the point contact transistor, it's this process, possibly the most important and significant technology advance ever. Without that, we would not have the system or digital revolution. So the digital revolution was, of course, due to the transistor effect, but what is really needed is a continuous process that can make predictive behavior of your materials and your transistors. And in the 60s, the industrial process became widely implemented. So from the perspective of making nanocellulose filaments, not only from our research, but other groups' research on this, I see us as being on the level of 1947, somewhere approaching 1954. We have the potential, we can do very fantastic things, but we still need to make the next step. And coming back to this problem with repeatability, so this is how we produce the filaments in lab so far when it comes up to the things that were made and published in ACS Nano with super strong behavior. You lift them up, and this is actually quite impressive. They are lifted up to a meter here, and this is 99.7% water that is lifted up. So you pick these up and you can mount them and you can test them, but it's still not super continuous. And when you do this, we actually know that we have kind of good control. We know the size and how this should look like. We actually can do simulation of behavior of the CNF gel threads. We can predict the shape. They are nearly elliptical or actually cylindrical when they are dried. There's actually a surface tension behavior that is good for us, and we can know that the estimated diameter after drying is 7 to 8 micrometers. But if you took these hand-lifted filaments that we saw in the video a couple of minutes ago, what you can see is to the left, variations in diameter of these filaments. And to the right, you can actually see the fiber diameter to stiffness behavior. And we have done, honestly, quite a lot of filaments to this date. That has been hard work, and it's very manual. The average diameter that we get is very in line with what we should get from a material continuity point of view. We can see that we have these huge variations in properties. We have strong filaments, we have weak filaments. You can repeatedly make very strong filaments. We see that the fiber diameter is not the one that decides really if it's strong or weak, but we can see that other things seem to control this. And this is to the right is a graph showing different mechanical performance as an effect of surface charges, concentration of the nanofibers, counter ions used, and so forth. So what we have done recently is trying to address this together with RISE bioeconomy. And what we have had a scale-up project operated for about 1 year with the goal of parallel fabrication. You want to do more than one filament at a time. You want to dry it fast. You want to spin it faster. You want to handle nanocellulose. And as I said, that was operated by RISE, but has been in close collaboration with us at KTH. And this project has been quite successful. We're still battling with these batches of nanocellulose to keep it constant. But I want to show you a short, brief video of what is being done now in this, has been done in that project. So the project was called NanoC Spin. And what we see is syringe mounted. We have a continuous flowing system where you can pick up the nanofiber or the fibrils that are the filament that is formed of the nanofibers. And these can then be taken further, and you can dry it and wind it up as a continuous process. So this is not only a way of making the continuous filament, but that is also helping us to get constant performance without this lifting up by hand effect with constant diameter. So this is a step both for volume production or fabrication, but it's also a step for ensuring constant performance of filaments. And as you can see, you can make taus of them, and these are you can actually start to work with from an engineering perspective. So this is what we're working with right now, and we are starting to get closer to this goal. We are not there with the Atala comparison with the transistor. We are not in a final process, but we are in a better state. And this is, of course, something we don't do together. This is actually a huge team effort. So this is something that's done together with KTH, and that is together with Professor Lars Wågberg, and Fredrik Lundell is part of we have a research group together with Professor My Hedhammar. I put in also Nitesh Mittal, who has done a lot of this filament spinning, and Thomas, who's working with a lot of characterization of nanocelluloses. We have people working at RISE Bioeconomy, Carl Håkansson and Andreas Fall. And then we also have international collaborators with Professor Nicholas Kotov in University of Michigan, Ann Arbor, Professor Stefan Roth at DESY, and Professor Benjamin Xiao at Stony Brook University. So this is the challenges we're working with, and we're getting closer, and hopefully we are breaking the sound barrier and this continuous process eventually. So with that, I would like to close my presentation and open up for discussions.